This video is a continuation of the topic motion graphs. In the first video, I defined what a graph is and I quickly showed how to draw a velocity time graph for a falling body, a body that falls from rest. And I showed you how the velocity of the body vary with time. I also showed that of displacement against time and displacement against time squared. Now in this second video, we are still going to look at this velocity time graph. The body at point A is dropped from rest at t equals 0. Of course, you know the initial velocity of the body is 0 and it falls a distance h above the ground to a point B. Let's say it falls for 4 seconds and attains a maximum speed of 40 meters per second just before it hits the ground, which means the speed of this body is given 40 meters per second before it strikes the ground. I told you that when the body falls from rest, the speed is greatest just before it strikes the ground. Okay, how do we calculate the total distance falling? Now, the distance falling by the body is determined from the area under the graph, the shaded portion. So sometimes we can give you the graph and ask you to calculate to determine the distance falling by the ball, because the ball starts falling at this point O, and where it hits the ground is this highest point on the graph. So this is where the body strikes the ground, because at that point the speed is roughly 40 meters per second. So the area under the graph, the area is bounded by the graph line, by the y-axis, which is called the ordinates, and the time axis. So the distance falling by the body, distance h falling, is half times base times height. That is, so distance h is half times base times the height of its shape. So h equals half times the base is the time, that is 4. The height is the velocity, which is 40 meters. So that the height falling by the body will be given by, this gives you 2 times 40, that is 80 meters. Okay, so sometimes we're given something like this, give you the velocity time graph for the body, and you'll be able to determine the total distance falling by the body from the velocity time graph. Okay, so we proceed to look at the two other graphs. That is number 4, I think that's number 4, the height time graph. How does the height of the body vary with time? Height time graph. How does it vary with time? Okay, so let's say that, of course, you know that if I come back here now, while this body falls towards the ground, the height reduces. The height is always measured from the ground level in the upward direction. So the height of the body reduces as it falls towards the ground. And does it reduce linearly with time? That's what we want to find out. So let's see the sketch of the variation of the height of the body against time. This is usually a question is set for some time now, past years. They usually set this question in WAEC. You see a body drop, a stone is dropped from rest from a point 8 meters above the ground. You see sketch a graph to show its variation, the height. How does the height vary with time t? And then they'll say, how does the height vary with time t squared? Now, if this point, because if I take this x time axis rather as the ground level, that is the plane, the ground plane, then from this point, of course, that is 0 meters. As I get to this point, let me call this point the height from which it starts falling. Let's say this is your 80 meters. 80 meters. So the graph will vary in a non-linear way. The variation of the height with time, not time squared, will be non-linear like this. So it's also a parabola. So this is the height of how the height varies with time, h is equal to half gt squared. That is the equation of the graph. Okay, so it does not vary in a linear fashion with the time t, with the time t. Now let's see, how does the height vary with the square of time, height versus time squared, height versus time squared. Okay, so we see here that the variation of the height against time, let's quickly look at that. T squared against h. Now let's say the body starts falling from this point, h meters above the ground. I take my reference axis again as my t-axis as the ground. Now the equation is still this t squared, meaning that I'm plotting h against t squared, against t squared. So the graph will not start from the origin, because at t is equal to 0, the body has some height above the ground. This is your height h. Let's say for instance 80 meters. From this point to this point is like your 80 meters. So what is the height falling after 1 second, 2 seconds, and all that? The graph is going to take this shape, a straight line graph, because it's a variation of this is where the body strikes the ground, and that's variation of the height falling by the body against time t.